And the way the course is set up, one of you will be considered to be the leader, and then the other one would be, I guess you'd call it follower. And then what are we going to do all the time? We're going to swap. And what are we going to do with teams? We're going to swap teams. So that means everybody is going to have an opportunity to work with everybody in the class. Because that way, what happens, and it's inevitable, is that you have certain people get together. My biggest problem is you have the people that are extremely adept at doing this. They want to work together, and the people who's having problems work together. In this class, it's not set up like that. You constantly move between groups. So everybody gets an opportunity to work with people that's got different personalities, which is something we're going to have to learn with. Of course, this class is pretty good, but eventually when the class gets more and more people in it, we're going to have conflicts. You know, that's just the nature of it. Yeah, I know you are. Everybody. Everybody in this class is. So what we're going to do first is we're going to start off with safety. So this is our first lecture. So we'll do safety, then we'll let's not do that. Let's do the way. So we saw the lines or the line. We'll probably look at the other one later on. This is safety. This is our safety section of the course, and we'll look at two industrial standards: the OSHA 9010, and then the National Fire Protection Association 70E. These are electrical safety standards. So topics we'll be looking at, of course, is electrical hazard and injuries. We'll look at OSHA 90, which is their main safety document, but subpart S basically deals with electrical safety. And we do have a copy of that, by the way. Go get it. We'll talk about the different boundaries that 70 gets set up and the personal protection equipment, which most people commonly refer to as PPE, and not actually implementing. So, by the way, most of these slides came from somebody else. I just plagiarized this. Some of it's mine, some belong to somebody else.
As long as you acknowledge you plagiarized.
Yeah. You're right, as long as you give the right references. But I need to go back. I'll find out who actually I got this from. I do need to put that. This is came off the Electrical Safety Foundation International, which you have access to this too if you want to go and look at some of these statistics. The last time they updated or published was way back in 2010, even though they still keep records. I don't know how often they update these. But 1,738 electrically related fatalities between 2003 and 2010. By the way, the trend since 70E came out, by the way, is that it's starting to do drastic drops. 13,150 severe injuries. 80% of the electrical injuries are caused by arc flash, and so electrical injuries can cause cardiac arrest or respiratory failure, and both those will kill y'all, right? You understand that. Muscle, nerves, and tissue destruction. If you do any research on the internet about people who've got severe shocks and electrocutions, you'll see it does some bad damage, does some real bad burns when it travels through the body. Burns, thermal burns, secondary injuries like to your ears and your eyes and stuff like that, especially when you get an arc blast. And of course, I found this is mine. Well, it's not mine. I got this from work too. Electrical shock. So what we'll deal with is electrical shock, and then some of the results we have of short circuits, especially in a high energy circuit. So when the current passes through your body is on the inside. You're more like a semiconductor, very low resistance. So we got to be real cognitive if we got any cuts or anything on our fingers. And of course, the path the current takes through your body. When you get into an electrical circuit, you are considered to be a load, right? You understand that. And then, of course, what determines how much energy you produce depends on the voltage you get into and the amount of current flow that's through your body. Everybody understand that? Another problem we have is that our brain, so we're bioelectric. Don't know what that does that mean? We produce water. We produce electricity, but we do it through biology, right? Our brain controls everything through electrical pulses. If we override those pulses, so if the energy I get into overrides the amount of energy my brain can do, then we lose control. And of course, one of the main things is your lungs. Right? If you can't breathe, you're going to die. Right? And our heart. If we mess up our heart, it stops beating for any reason, then we're going to die. So these are anything that goes through your lungs or goes through your heart. This is the most drastic steps of places that current can flow through. And this just shows you some of the paths. In the next slide, I'll show y'all some paths. So what determines is the path through the body, the amount of current flow through the body, and the length of time the body is in circuit. Everybody understand that? Body electrical resistance. What determines how much resistance you have in your body? Well, there's some up here, right? Wet or dry, right? Open wounds, closed. Where do you come in contact with? What would you think the worst place to come in contact with the circuit? That's dangerous, but that's not the worst place. The feet that has the place that has the least resistance. This is pretty dangerous right here, ear to ear. Very thin, very thin skin right here. Hand to feet is actually a more dangerous path. This itself is not good if you get into a high enough voltage. This is going to take care of you because this definitely takes you to the heart, right? You understand? But it has a pretty high resistance. Your fingers have the thickest skin, so this is where your thickest skin is out on your fingers. Hand to hand, hand to foot, foot to foot, hand to elbow, and etc. Right? Wet or dry. So your body resistance is a lot lower if you're wet. Your body resistance is a really lot lower with sweat. Sweat has salt in it. Salt is a really good conductor of electricity. AC or DC. So there's a difference between AC and DC. Then we get into AC, we're not only concerned with how much voltage, but the frequency that voltage is at, trying to push through it, right? Push current through it. Are we okay? So these are some sites. This is pretty good information that shows you the most dangerous paths. Hand to hand, right? You understand that? Leg to leg, okay? And then leg, arm to leg, or arm to leg. Each one of those will cause you problems. Either they're going to affect your lungs or they're going to affect your heart. This makes sense. This shows you some basic body resistance. You see ear to ear is only around what? So this is calculated current. 110 volts. If you got in between 110 volts from ear to ear, it's about 100 ohms of resistance. Well, you stick your head in there.
I mean, you'd have to
You'd be surprised. I was out at U.S. Steel, and I took my hard hat off, and I leaned up and got into a disconnect with my head. And that's probably why I stutter a lot.
I mean, I can understand you touching one ear, but to actually get a current flow through both ears, you'd have to try.
Dry skin is pretty good, around 100,000, 600,000 ohms. So you'd have to get into pretty high voltage there. But look, where we at? Dry skin, wet skin, head to foot, we can guarantee about what? 500 ohms. Wet skin, you're going to get down in at least half what you got. So this is why people say working in wet environments really causes you problems. I think we got threshold currents. This is pretty interesting chart that I found on the internet, which shows you the different currents, and this is an average, and it looks like women have a higher body resistance than men. because look, our tolerance to this. So men, if you get into a slight sensation, you start feeling it around 1 milliamp. Let's see, where's women is what? 600 milliamp. Guys are 400 milliamps. Ladies are what? 300. So but it looks like that according to this chart that women have less are more susceptible to feeling electrical pulses than guys are. But also notice as the frequency goes up, the amount of current you can get into appears to go up, which is pretty interesting when I look at the chart. So on the first one is 60 cycles, which is very, very important because our power grid here in the United States is 60 cycles. Everybody said y'all had AC over 10 cycles. But if you get into 10 kilohertz or 10,000 cycles, then the amount of current your body can take would be 7 milliamps, which is pretty interesting. Don't ask me, this is not my chart, but I saw it in more than one place. Threshold of pain gives you the threshold of bodily perception, pain and involuntary muscular control, DC, and another thing is we are less susceptible to problems with DC than we are with AC, which was pretty interesting when I started researching this, which is pretty neat. So when they start saying this and that about, what is dangerous current, usually we say anything above 50 milliamps is considered to be a fatal current. But is that true? Well, no. It's going to depend on whether it's AC. It's going to depend on whether it's DC. So basically, when you read about 50 milliamps, that's just basically a rule of thumb, right? You understand that. So these are pretty interesting charts. Pain, we get into 76 milliamps or around 50 milliamps for women for loss of muscle control. This will be the third one down. This is where we really start getting into problems. Is around, and this is why I guess 50 milliamps is a really good shot. This is around the threshold for minimum threshold for women. It looks like AC is less susceptible to DC. Now AC is kind of picky when we start talking about the past. So it's real hard to come up and say exactly what current is going to give you. Because if you get something flowing through your heart is controlled by electrical pulses, right? So the rhythm of your heart is controlled by electrical pulses. If you override that, then your heart is going to try to beat at the frequency that you get into. And if you get into 60 cycles, and you get enough current through your heart where it overrides what's available from the brain, your heart cannot beat 60 times a second. Most people's heart beat regular around 60 to 70 times in a minute. So what happens if your heart tries to beat that fast? It goes into what we call fibrillation. What's fibrillation? Now your heart's out of sync. Your valves and your heartbeat is out of sync. So your valves are opening at different times when they're not supposed to be open. They're closing at different times. So you lose blood pressure. Very, very important. So these are the two basic sets. The 1910, I don't know why I got 9010 in my head. It's probably going to be in some of these PowerPoints. But 1910, this is the OSHA standard that covers safety in the workplace. And then NAFTA 70E, which basically covers electrical safety. So the 1910 covers basically all kinds of standards. It's got all types of subparts. And then the 70E is strictly for electrical. Are we okay? So I said 19. So that's supposed to be what? I knew I did that. So I gave y'all the answers. Is 1910 law? It's OSHA. OSHA is law. OSHA is law. If OSHA adopts anything, it is federal law. Is the National Electrical Code? Huh?
That's a standard.
Is no. It can become law, but whether it's law or not determines if it's adopted by the authority having jurisdiction in the area that's responsible for that. So if you work in Birmingham, and then the electrical inspectors in Birmingham, if they decide to accept the National Electrical Law, then it's law in Birmingham. But that don't mean it's law in what? Jefferson County. Y'all understand that? So OSHA is basically a standard, and it does not deal with, and we'll look at this. Now 70E is this law. Yes, if you work for the Department of Energy. If you don't work for the Department of Energy, then 70E is not law. So when you start looking at the 910, the subpart S, you'll see that just about everything in that is taken care of in 70E. So if your company honors 70E, then they're going to meet the requirements of 1910. That makes sense? Yeah, so most people do 70E training because they know if you do that training, then you're going to be ready for what? You're going to comply with the 1910 subpart S. A lot of people get confused with what the National Electrical Code is. This is a regionally adopted standard for safe what? Installation of electrical wiring. So basically, this basically takes care of how you can safely install stuff. The standard really does not say, okay, this amount of current, this PVPP, these meter requirements. It has nothing to do with that. It just covers the technique of safely installing equipment. That makes sense. So 70, the NEC would specify where a disconnect would be, right? So it says a disconnect has to be within a line of sight, or if it's not in line of sight, it's got to be within 50 feet of the unit itself, right? Does that make sense? But it don't say, okay, if you got to lock and tag that thing if you're out there working on it. So 70E. This is put out by the National Fire Protection Association. So we call it National Electrical Code, but it's actually a committee of the National Fire Protection Association, and it's actually NFPA 70. So that is the National Electrical Code. 70E deals with electrical stuff. That makes sense? So we'll look a little bit at 1910, and what you'll see is there's a lot of things that coincide with these two. And we don't have a copy. By the way, this link it's available to you. You probably won't be able to do it off of, but this is 1910. So 1910 is a free document, and this is 1910. So you can see what it covers. I mean, it covers almost everything. Walking surfaces, means of egress, platforms, ventilation, but we're concerned with way down here is subpart S. And subpart S, until I get there, it's the 300 standard. So subpart S is what? So subpart S is strictly electrical. Are we okay? So the little sections that we'll look at right now deals with subpart S. But there's a link right there if you wanted to go look at the 1910 standard, and you want that big document right there. So subpart S deals with electrical safety installation. So this gives you the dots. It's got a lot of space in there that's reserved. How they come up with those numbers, I'm not really sure. But for some reason, I guess they have a standard of the way they lay stuff out. And so the 330 and every one of them would basically contain the same information. Well, if it contains information on walking on wet surfaces, then that wouldn't be part of the electrical. So what do they put? They just put it down as reserve. That makes sense? So if you look at the 910 standard, you can see 308, 309, 310, there's actually nothing in there. So if we could bring those up, there would be nothing in there. So they just put them down as what? Reserve. So 331 deals with workplace practices, which we're going to get in. Then 399 is your definition, and then we have duties. Right? So 331 talks about what? Premise wiring, connecting supplies, wiring, and then it deals a little bit with fiber optic cable. It does not deal with the generation, distribution, or communication standards. Fiber optic cable does not carry voltage. It carries light. But the materials that fiber optic cable is made out of is where you get into problems. Like the core or the actual conductor of it, of low opposition cable is made out of glass. And the glass is it's thinner than the human hair. And sometimes if we get into some of our techniques, they use laser to send information through there. If you look at a laser beam, it's got enough intensity, it can cause damage to your eye. So that's what they're looking at here. That makes sense. Probably not so there's really no power involved.
That's what I was thinking. I'm kind of surprised to see it up there.
Yeah, undoubtedly, fiber optics is a relatively new technology, and I think what happened, and this is just Rich's opinion, is they needed to put it somewhere instead of making a whole sub part that deals strictly with fiber optics. But if that's what happened, I don't know. This is a qualified person. So this is something we need to know. One who has received what? Training and has demonstrated skills and knowledge in the construction and operation of electrical equipment and installation and the hazard involved. So that's basically what we're doing this semester. The training employees who face risk of electrical shock. This is covered in table S4, which is on the next slide, by the way. This is what I wanted to make sure that we, or any other. So these are the trades that 1910 is specified as being susceptible to safety concerns in the electrical field. And you can see we fall into just about all of them, okay? Especially assemblers and electronic technicians. So that means we are required to provide some type of training. Now, literally in this class, we would not have to, but this is a perfect place to put it. Especially it's in the plan of instruction approved by the state, because we're not working on anything that's greater than 50 volts. So the magic number is 50 volts. Above 50 volts, then we're going to have to start considering personal protection equipment. We're going to start considering lockout, tag out, working on live equipment and stuff like that. So if it's below 50 volts, you can work on the equipment while it's energized. If it's above 50 volts, then you can't work on the equipment when it's energized. Now, work on means to replace things, right? Of course, testing, we can test on live equipment, but we can't do what? We can't work on. Y'all understand the difference? So we can't replace things that on a live that with the circuit with power applied. We cannot rewire things. We cannot cut wires. We can't do anything like that with power applied. But we can test it, right? Y'all understand? Training focuses on recognizing live parts, determining voltage of live parts. It always bothers me when people go out and they'll hit a disconnect and then they go out and start working on something without getting their dang meter out and checking to see if it's disconnected. For one thing, they might have pulled the wrong disconnect. Another thing, the disconnect could be defective. A disconnect is an electromechanical device. And it can do what? It can fail. Okay, y'all understand that? Clearance distance specified in 330. We'll look at that. Focuses on near exposed energized equipment. Locking and tagging, which is going to be our first lab. De-energizing. De-energization. Then doing what? Verifying. So that's what these meters are for. You need to always verify that your disconnect, that you pull the right disconnect, right? And then also that the disconnect itself is operational.
Let me ask you this. You pull the disconnect or something, it's got a display, LED display, and you see that LED display go out. You never use that for verification.
No, the way it's written is that you always verify with the meter. Always. Which makes sense because it's a light too. You know, who's to say that the light didn't blow at the instant preceding?
I know you still the worst of it. Like magnets, look like them off. The light will have you assume that magnets.
And that's the problem with lights. Lights can blow. And when do they blow? Well, they usually blow when they change. When they try to change from off to on. Well, usually they blow when they try to change from on to off.
I was just curious, like, the 770 display. Except for all those blow.
I don't know. That's like I said. All I know is that when you look at 70E, they say verify de-energization. Every place I've read, it's always verify with the meter.
Well, the reason I had Mercedes guys, the pallets that carry the cars around, right on, it's powered by Greenway. You got 300, L2, L3, Green. And they'll open the door to the gauge, whatever, which gives all power in that rail. They always look at the box, and that box, after lost all the lights on, so
I don't think 70E says that's legal.
that's the reason I was curious.
What I've read is it always says verify, and it usually says with a meter. If you could verify with a light, then because I'm pretty sure one of these little voltage detectors are legal. Voltage detector is just a unit that picks up AC induction,
Right.
verifies if a voltage is there. I think that's should be. Overhead powers. We got a video we're going to show y'all where some guys are moving a stand. I don't know if y'all seen that before. And get into some power by moving a metal stand outside their workplace, which is pretty interesting. Illumination and then several other tasks. De-energized parts. Live parts to which employees may be exposed shall be de-energized before employees work on or near them, unless the employer can demonstrate that de-energizing introduces additional increased hazards or if infeasible due to equipment decision or operation limitations. Live parts that are operated at less than 50 volts to ground need not be energized if there is no increased exposure to electrical burns to explosions due to electrical arcs. So what this says is that if it's below 50 volts, we can work on the light. But if it's above 50 volts, you cannot work on the light. Well, it don't say you have to.
Oh, I know
It
that.
says you can.
I'm just saying, you go right ahead.
Yeah, and that's right.
I'll sit back here and watch.
So if I was an employer, and my whole shop was less than 50 volts, and I told you to go out and fix something legally, you really have no argument. Now, but if the guy come up and says, well, I think it's unsafe, and then the employer, then he might get into some legal problems.
Mercedes goes by that. Well, they all their control modes.
Yeah, well, that's becoming very, very popular.
And you can get them 480. They make it difficult
Covers portable equipment, plug and cord. Y'all understand plug and cord, right? That's what most things are. So plug and cord. Reclosing circuit and inspecting equipment. PPE, personal protective equipment. 70E really gets into what's required, what type of PPE is required for your application. We're way down, still low on the scale, but still, even in our place, since we're going to be exposed to 120 volt outlets and stuff like that, and we're going to require to have certain PPEs. Now it's very low, but stuff like shorts and sandals and stuff like that is not going to be allowed in the slab. Understand? Safety devices. So it's not very, very much. When you take motor controls now, you're going to have to buy some leather gloves to work over there. To make measurements inside that 208 cabinet, you're going to have those. Anytime you make the voltage measurements, you'll have to put on your gloves. Anytime you're rewiring or stuff, and because we're a class Z, that's class Z. So that's pretty much just a little talk about what the 1910 standard is. Even though sometimes I call it the 9010, and sometimes I call it the 1910. Everybody okay? Anybody need a break? Okay, let's go ahead and take a break. 70E. And we don't have a copy of this. We need to look at getting one. But basically, 70E covers safety for you. So the National Electrical Codes cover safe installation of electrical equipment, right? You understand? And then they realized that there was really no standard that protected you or the electrician or the electronics. So it covers electrical shock, arc flash, arc burns, thermal burns, and arc blast, which are so arc flash and arc blast are two different things. But so arc blasts are the results of some arc flashes. Arc flash, these are electrical short circuits. So arc flashes are called by short circuits. Arc flashes from exposed conductor to another conductor or to ground. Sometimes it's so small you can't even see it. But you start getting into these plants where they got these high energy circuits. That's when it becomes extremely dangerous for short circuits. Arc blast is the pressure wave caused by an arc flash. And I mean, it's a blast. So the blast itself could damage your ears. The flash is extremely bright, so it could damage your eyes. So this is the yeah, and that's what happens. And we'll look at this. I'll talk about the temperature of an arc blast in a minute. This is what's coming. Concentrated energy explodes outward. High intensity flash, which could damage your eyes if you don't have any eye protection on. Could burn your eyes if you don't have safety on. Temperatures can reach 35,000 degrees. People, that's hotter than the sun. So if you get temperatures that high, what's going to happen with any metal that's inside that blast? It's going to melt. And now you got, not only do you have the blast, but now you got all the shrapnel heading. Pressure waves can reach 200 pounds per square inch. So that means 200 pounds of pressure here. Well, if it comes up there and it hits my whole body, ain't no way in the world I'm going to be able to stand up on that, right? What's going to do? It's going to knock me across the room, right? Vaporizes conductors in copper and explodes particles like buckshot. And this is where we used to have most of our accidents at right here. Most fatalities were the cause of this. And this was one of the things that 70E really wanted to bring up. Arc flashes, severe burns, broken bones, vision damage, hearing loss, brain or internal injuries, punctures and lacerations, and of course the ultimate is what death. And we're not trying to scare you, man. If you every time, when I was in the Navy, every time we had a big, holiday like Christmas and everybody took leave, we would have what they call a safety stand down, where they would we wouldn't fly planes and they would bring us in there and they would show us these Ohio State, sheriff's, car wreck videos, where they'd be pulling people out of these cars and they'd be all limp, their necks would be laying over and be gone. And then everybody gets out on the interstate and they drive 30 miles an hour. So, if you want to be scared of something, be scared of getting in that dang car and driving around. That is dangerous right there.
U.S. still uses truck cells, big, huge circuit breakers.
That's what we're going to look at in a minute.
Supposedly, somebody decided to jack one out and it didn't get a load of it. And they said that he jacked that thing out and it pulled, separated, it knocked him and the truck cell clear through, like that.
Yeah, that's what they call racking and unracking, those big breakers like that. And that's what we're going to look at here.
I think it's 6,600 volts.
I don't know. Somebody was telling me. So arc flashes are caused by short circuits. Improper training, improper working procedures, dropping tools, accidental contact with electrical system, installation failure, short circuit protection, voltage testing, or inappropriate equipment. You'd be surprised how many people get killed by their meters. By putting a meter into a circuit that's not rated for the circuit they're measuring. And then it blows up and then it creates a short, right?
It's better now than most meters.
Well, that's why things have changed. It's a lot better now. And that's why we look at categories of meters and we don't buy them from Harbor Freight. But buildup of dust, this was the danger we had out in U.S. Steel because most of the dust out there is conductive. It is fine, and it's improper maintenance, sparks produced during racking of a breaker, replacement of fuses, and so these big breakers, when you push them in, taking a breaker and install the breaker, that's called racking. And when you take it out, that's called unracking or deracking, either one of those, and that's where a lot of accidents happen. Inattentive overconfidence. So you get these people that first of all, they'll go into these dangerous situations. They like these attaboys, getting lines up and running real fast. They like these attaboys, and they'll go flying into some place by themselves. And they're in there by themselves. And then they get into a situation they can't. There's one, Eddie, I got to look it up. They don't actually show it, but it's just the people talking about all the stuff he did wrong to get killed. Most of the time, it's you getting yourself killed.
I mean, would you tell it in attendance or places? You do the job.
Well, that's what overconfidence is. I can fix it. I can fix it. Wait for Eddie to get here. Well, I can fix it. I can fix it. And a lot of them, and that's just in our mentality. That's something that we gotta get out of, and that's what it is. Overconfidence, thinking that you don't need help, that you can work on 23,000 volts while it's live. And take a standard meter and put it into a circuit right there. This is racking a breaker, and this is a fatal accident right here. This is up on YouTube. So we'll go up there.
We go to this PowerPoint to do the quiz. The safety.
No, this safety. This will be. Where's full screen at? I don't hear any. I didn't bring any speakers. But this is racking breakers. For one thing, this was silly because you see that hole in the wall. You see that hole right there in that door? You know what that hole's for? To rack that breaker with what? With the cabinet closed. So they're racking this breaker. They're racking this breaker with the door open. And one guy's lucky, the guy that's racking it right now. So basically, it's a screw gear. They got a thing that they spin, and it just racks it and moves that breaker in. Yeah, well, they have different ways you rack breakers. They have motorized, a lot of them racking. So this guy's saved his life right this guy in there racking it out, he's the, that's an arc flash and an arc glass.
Did they find the guy?
FIR, yeah, he was on fire. No, they didn't fire him, he killed, that's a
No, I
fatal.
said, did they find him?
Oh, finding part, I don't know, I just knew it was a fatal, it was a fatal, it was a fatal accident. But that was just, of course, this was before PPE. There's no PPE on, so somebody racking the breaker with that much energy.
He did have a face shield.
Well, he did. You saw him put it down. Yeah, I don't know if it was face shield or glasses. I couldn't tell.
It looked like he wore a face shield back.
But somebody racking a breaker with that much energy, they would have been required to have a glass suit on. And we'll look at some of these glass. This might be the one that shows these guys. They show guys working. That's really interesting. They wear. This is a test where this is not a person. This is just showing, so they deliberately created a arc glass in this video right here.
Right to it, didn't it?
Yeah. Now that's a mannequin, so that's not a real person. But so you can see the danger when you go working on some of these companies. Look at his glove, not his glove off, it's still falling over there. Might be. Didn't look like it, but it could have been. There's all types of videos, by the way, if you get on the, you just look up arc glass, arc flash. So NAFTA, basically the same definition in 70E that says one who has skill and knowledge related to the construction and operation. So that's good. So you don't need to be working on something that you don't know what it does, right? You don't understand that. So that's one of the things we're going to learn how to do. Most companies have what they call a break-in period or apprentice period where they put you with somebody and you go around with them. U.S. Steel did that. I think U.S. Steel was, when I was there, it was like 6 months. That before they put you on what they call standard rate. You never work by yourself. You always work with somebody. And what was nice about U.S. Steel is that the more you knew, the less person that was teaching you had to do. So they would tell you everything. I mean, they would. So it wasn't one of those things where they were scared of their job. They wanted to tell you because the more you knew, the less they would be called in. They could sit back at the shop and say, "Oh, Rich, have that. He's the newbie, right?" An operation of electrical equipment and installation and has received safety training to recognize and avoid hazard involved. And so you're working in a trade that's dangerous, right? It has the potential, but it's probably less potential than you getting killed in a car wreck if you just do what. And what we say, if you always obey the laws and you always stop at red lights and stuff like that, it doesn't mean you're not going to have an accident. It means your chance of having an accident goes way down. But if you never stop at red lights, you're going to have a wreck, right? So if you don't do basic safety, then sooner or later you're going to have a wreck. It's just like these people you see weaving in and out, in and out, in and out. They're going to have a wreck. Sooner or later they're going to have a wreck, right? They might not have it today, and they might save 10 minutes on getting to work, but eventually they're going to do what? They're going to have a wreck. Understand specific electrical hazard, knowledge of and construction of the equipment and operation. Identify and understand the relationship between the electrical hazard and the possibility of injury. Distinguish exposed live parts. Make sure you understand what, if they're exposed and they're live. Able to determine voltage of live parts. Understanding complies with our flag and shock boundary hazards or hazard boundaries. Being able to know know what you're getting into before you get into it, right? Know what voltage. Don't use a meter to see what's there. Use a meter to verify what's supposed to be. So before you put a meter in a circuit, you're supposed to do what? Know what's there. We had a brand new meter, just brand spanking new. It was a new version by Fluke. And we decided we wanted to measure the voltage on a laser. We had no idea what it was going to be. As soon as we put that meter in there, fired that laser, smoke came up through the meter. Now that sucker could have blown up, right? You understand? But that was, whose fault was that? Was it the meter's fault? No. It was me not realizing that that laser had over 50,000 volts out there on that anode grid, understanding that. So I had the wrong test equipment for that, right? You understand? So that could have been, luckily there wasn't a lot of energy, it was just actually a voltage potential. Luckily the meter was a brand new meter, and they were still doing the failure rates on the meter, and they swapped the meter out. Luke swapped the meter out for free because they wanted to take it apart and see. I can see what they're saying. What in the world is this guy doing? We had a teacher when I was going to. We had a teacher here that wanted to measure the voltage, the arc voltage on a arc weld. So we got one of our nice bench Fluke meters and take it down and put it on there. And, as soon as that torch arced, the meter started flashing. It wasn't because of voltage; it was such a high frequency that thing generated. It wiped out the high frequency section of the meter. No, that was it. This was Jack Walker. I don't even know if Dennis was working here at that time. Proper use of precautionary techniques, PPE, includes arc flash and shock protection. Insulated tools demonstrate how to select and use a voltmeter, which we're going to look at here in a second. Decision-making process used to determine the degree of extension. 70E has really made a big step in meters. So I've got meters, and if you pop the back of the meter, you'll look and see the battery and the fuse of the meter right there together. Now the fuses and the batteries have got to be separated. So if you've got into a new meter, the fuses are actually in little indentions. So if a fuse arcs, it won't get into the rest of the meter, right? Does that make sense? So there's a lot of it, really been a lot of improvements in meters since I've been here. Energized electrical conductors and circuits parts to which an employee might be exposed shall be put into the electrical safe work condition before the employee works within the limited approach boundary of those conductors. So that means, it doesn't mean if you pass by it, you got to do that, because now they've set up these boundaries. And as long as you're outside that boundary, you don't have to wear PPE. But then they've got like 3 or 4 different boundaries where you got to put different equipment on depending how close you get to that circuit and how much energy is available. And this has got to be true unless the employer can demonstrate that de-energizing introduces additional hazard or is infeasible. So a hospital, it would be impossible for a hospital, because they kill the energy to the hospital, they not kill people, right? So if you're in that situation right there, you could probably prove that it's so that you can prove that it's going to be to let people work on energized equipment. But on normal manufacturing, like Mercedes, there's no way in the world shutting down a line and not putting out a car is going to be worth not being able to be. They're justifying somebody getting killed by electrical shock.
But nowadays, they isolate every circuit on motors.
And 70E has caused that. 70E has caused that. 70E is the one that's caused hundreds of disconnects and stuff like that. Systems are designed now where they build in buffer sections. So if this part of the line starts, they got someplace they can stop this until the other side of the line comes up. So 70E has basically been a big result of that. Interrupting life support, deactivating emergency alarm system, shutting down hazardous location ventilation system, like in Ghostbusters, the first Ghostbusters, where the guy killed the pilot to the containment unit. So that would be the condition where you could do that. A circuit and conductor operates at less than 50 volts. these are the guys that, so we are the guys that can go past this route because we are responsible for what? Testing, troubleshooting, and measuring those. But literally, that is the only time you should work on a live piece of equipment. So you go in there, you take your tester, you make voltage measurements, you determine what's wrong, right? Or take a shot at it. You kill power, you lock it out, you replace the part, you do wrong. Yeah. Kill the power, verify there's no voltage, right? Replace the part, energize it. Everybody okay? So we can test it with power on. We have to do that. There's no way in the world you're going to troubleshoot with power off. You can't figure out why something's not working if you don't see what it's doing, right? You understand that? So we are the exception. De-energized lockout policy. So we're going to do that in this class, even though we're below the 50 volt standard. We've got plenty of locks. We've got plenty of tags. So when you're troubleshooting, you're going to be able to use the meters when it comes time to rewire something or replace something. What are you going to do? You're going to lock and tag. All power sources. 70 only determines the energy, but lockout tagout means to lock and tag all sources of power.
Do they really push the tag now?
That is, it's called lockout and tagout for a reason, because legally I cannot remove your lock. Now we're going to do that. For one thing, locks cannot be combination. They got to be locked.
One key on, or key and one key on. Let's see. U.S. still changed to say to lock out triad. They didn't require tags. One company I used to work for, you had to have a tag and a lock. The U.S. still, we didn't have a single tag. You had to lock with a little brass tag or a lane.
Well, I guess that would be. Well, I think they've actually put the information on your tag.
So that's the reason I was wondering, do they actually?
You did tag out. It's just that you didn't use a standard paper tag.
Right. Well,
You had all your information on the wall, on the key, and that's basically what. So the information. Well, I don't know if it had to be on the wall.
Well, U.S. did. They had a particular lock with them. If the safety locks were issued, they had lock cases.
Yeah, they gave us a lock.
One key only. If you ever encountered a lock that had two keys, you were to throw it away immediately. It was to be destroyed. You had the brass tag with your last name and your badge number. That's all that was required.
On the key.
No, this was the actual lock. It was brass tag to put on the.
Okay, so that would meet the tag out condition. But what you're supposed to do on a tag out, you're supposed to put who the tag belongs to, and then basically how to contact. A lot of times there usually is a section so you can put the date the tag is put on there. But as far as I know, that's not required. But what is required is the name.
That's the reason I was wondering if they still use the tag out, because the first job I had, where I had to use lockout tag out, we actually had the individual tags. You couldn't attach it to the lock. It had to be attached adjacent to the lock. That way, if somebody else had a lock on there, that tag stayed with the equipment or whatever.
We was out there. We used regular tags too.
No, this wasn't the U.S. Steel. This was the first place.
But what I'm saying, but when I was out there, we used regular tags, but we kept them on our lock.
The only time we used a tag is.
Well, what I'm saying is, you use the tag. That brass, that was your tag. So all you got to do on the lock is identify who the lock belongs to, and basically how to contact it. Okay, and that's what's required on a tag. We're going to use paper tags here. So what I'm saying, that little brass thing that was on your lock, was the what?
Tag.
Was tag.
But I was just curious if people actually use the actual tags.
Oh yeah, like you said, that company you work for, they used.
That was pretty good.
Yeah, but that's probably going to be the. When I was out there, they kept two keys. When I was out there, this was before 70E. The boss got a key. So that inside the foreman's office, the boss had a key, and then we carried it. And they were the only ones that could remove the lock if you wasn't there.
When I was up there,
Yeah.
if you left work and left the lock on, they had to call you. You had to drive all the way back out there and remove the lock yourself. If not, there was like 20 pages of paperwork they had to go through.
Before they cut it up, yeah. Never reach into a blind spot. Work areas must be what? Eliminated. Don't wear conductive apparel. So, what does that mean? Y'all need to wear in here?
No jewelry.
Cotton. Yeah, when we was in the Navy, when we worked out on our airplanes, that was one reason we could take off our tags. We actually had to take off our dog tags when we went out to work. So we'd come in. I was an AE, which is electrician made, and we'd take off our tags.
I think they issued plastic tags.
Now, I don't know. The chain. We were working on this lady's stereo. Dennis Ramsey was working on it. I don't know if he's not. And Dennis had one of these cross pins in his shirt. We were over there. The lady was standing there that owned the stereo. It was a nice power amp, and Dennis leaned over, and that cross pin fell out of his pocket. And that was one of those slow motion situations. And it fell down, and it bounced about 4 times.
No.
The lady was standing there going, "You're going to pay to fix that?" I said, "I ain't going to pay to fix that." I said, "You're the one that brought it in and wanted me to look at it for free. You wanted to bring it," is what he said. He said, "You brought it in here and want me to look at it for free." He said, "I'll fix it, but you'll buy the parts," is what she told me. I don't know what happened after that. Use non-conductive ladders. So when our last electrical instructor was here, he bought all these nice metal ladders, 4 of them. And we can't use them anymore, so they had to go out and buy all the fiberglass ladders. We can't use them to work on electricity. We can use them. This is a typical art flash label. Once you have a assessment done, and basically this contains very, very important information. It tells you where your art flash boundary is. So if you're not working on it, this guy is very low. So this category 0 says you need to wear untreated cotton, right? Okay. So that means in this class we're not going to wear any synthetics. So if you like wearing jogging pants and stuff like that, they're not cotton. They're fine to wear to any other class, but we want you to make sure we're not going to wear short pants, sandals, no open-toed shoes. Of course, they require leather shoes too. We're not going to require that. All we're going to do is make sure we do no cotton shirts, right? You understand that? And also no short pants during summer. By the way, y'all signed the locker when y'all get to it, right? I don't know if y'all use it. It's part of your things. Yeah. And there's some up on the second floor on A building that use regular standard locks. I think they would just all lock and use those. The other ones, though, they used to be assigned to the bookstore. They're probably not assigned to the bookstore. You probably have to ask at the business because the bookstore is not ours anymore.
My car is closer.
Yeah, but what I'm saying is, even then, taking like motor patrol and stuff like that, you can leave a shirt in there, you can leave pants in there, right? Do that. So go by the business office one day if you want a locker over there and ask them, because you pay for it anyway. I mean, it's not going to cost you anything. At least it used to. Limited approach is 42 inches, so that means if you work outside of 42 inches, you're not going to have any PPE. Once you start getting through these approach boundaries, you're going to have to start putting some safety stuff on. This is and that's so the flash hazard is out to what? 18 inches. These keep going up. This is a bigger, higher one. This is flash hazard boundary is now what? 156. So there's a lot of math involved in calculating these. Normally what a company will do is hire a service that comes in here and identifies it. It has a lot to do with it. The further you're away from your distribution, the less chance you have for arcs. So, like in this room, we got 120 volts. We don't have any high voltage in here. We don't have any 208 or 220 in here. So this would be a very, very low rating for this building right here. Plus, we are on the other side. We're inside the building, so our safety requirements are a lot less. Minimum, though, you're going to see is basically no shorts, no open-toed shoes, safety glasses, and then, of course, this is ours. So you have to calculate these calories per centimeter squared. This determines how much energy is available where you're working at. And the higher the energy, that you move up into risk categories. And of course, here you see that the highest risk is the category 4. What category do you think we are here? Yeah, we're category 0. Are you okay? Then the next slide, this talks about the different boundaries you're in, and then what PPE that you're going to require depending on what boundary level you're in. The closer you get to the actual energized equipment, the more safety equipment you're going to have on, right? Everybody okay? The qualified worker is responsible for ensuring physical barriers are in place and all approach boundaries are enforced during work. Limited, restricted, and prohibited.
Come here, look at this.
Yeah, hey, come here, look at me. These are the different color codes for this is for glove charts. So the lowest we've got is these. So now they've actually color coded the gloves that you can wear depending on what category of PPE you wear. The lowest one would be a what? Would be a beige glove, all the way up to an orange. Are we okay? Voltage rated gloves, first line of defense, choose right size. Leather protectors must be worn over rubber gloves. So when you get into the higher ones, you're required to wear rubber gloves. But then when you wear the rubber gloves, you're supposed to put what? You're supposed to have leather gloves on. Motor controls, since we're category 0, we'll have to wear leather gloves. We'll just use regular leather gloves. Because like I said, we're very low over there. What we're trying to do is just get you, we'll get you in the habit of looking at this. Before first test, every 6 months, tested but not issued for service gloves may not be put into service unless tested within the previous 12 months. There's a company over on Long Avenue, by the way, that makes these rubber gloves, that high voltage rubber gloves. It's really neat. And watching the way they test them. So they actually fill the inside of the glove with water and then the outside of it, and then they put a probe in each unit and measure the gloves to see how they do. And they're spinning while they're going down there too. It's pretty awesome. I don't know what the Salisbury video is. I'll have to look that up. Arc rated fire resistant clothing. Layers, outside layers must be flame retardant. We'll go ahead and look at this. It says clothing must fit properly, right, with less interference. So if you go out and you like these tight fitting stuff, this is not too good. Clothing must cover potential exposure areas, care and maintenance, inspection. We're going to try to offer a full set of this category 4 PPE. This is where we would be at. So technically, this is what you should wear. You should wear a hard hat, right? You should wear what? Safety glasses. You should wear ear protection. You should wear long pants. You should wear leather insulated gloves, but it says what? As required. And then leather boots. 100% cotton. Now this is for Cali. This is risk category Z. So this is it. This is the lowest thing, no matter where you work at. And you're honoring 70E. All your maintenance people are, and even your operators should be supplied with this basic equipment.
And you don't want to stress the cotton.
Huh?
Why they stress cotton, not polyester?
Because it's not as flammable, and if it does catch on fire, it's not going to stick to you.
If it catches on fire, it won't melt and stick to it. Yeah. Polyester, plastic.
We went through a section back in time where all the guys. This is anything that's got a rating between 1.2 and 4 calories per centimeter squared. So you got to have now. You got to wear rated shirts, right? You understand that? So you got to have a 4+ calorie long sleeve shirt, long pants, coveralls. So now your pants have got to meet the fire retardant standard, and your shirt's got to meet it, right? Safety glasses, arc flash face shield, hearing protection, VR rated gloves, voltage rated gloves, leather gloves, and leather gloves. Then we move up to 4 and 8 calories per centimeter. Looks the same, but you got to have a higher rating on your garments. So notice before it was a 4, now it's a what? 8+. So it's basically the same equipment, it's just higher rated. Then we move into 25 plus, which would be 8 to 25 calibers per centimeter. And now you're starting to put on what? You got to have arc flash hood, safety glasses, arc rated face shield, hearing protection, inserts. So this is saying you can't have what we used to call the Mickey Mouse ears that we would. Then voltage rated gloves, leather gloves, and leather gloves. Then we move up to 40 plus to 25 to 40 calories. Now we're really starting to get into flash related hood with flame retardant long sleeve shirts and long pants, safety glasses, arc flash shield, hearing protection, VR voltage rated gloves, leather gloves, and leather boots. And this is the bomb suit. And of course, it all depends on what. It doesn't depend on the voltage. It depends on when they come in and do that arc flash, and they calculate the potential of a arc flash. That depends on what type. So I'm sure, I don't know. The highest voltage we have on campus is 208. We know what they call it, ground block. So all ours would be a category 0. You get out to US Steel, I think their highest voltage is 6600. And then you start working on some of those disconnects and some of those motors and some of those things. And this is the type of thing we work.
You know, a guy from the JFG was 6 months.
Oh, really?
Yeah.
You catch them. There's one video where a guy dug into some underground cable.
It took 1.3 seconds to break. And that 1.3 seconds, wires, every piece of wire, rubber, he lived up out of it. He had burned.
Oh, really? And that's what they talk about you know, there's a lot of videos out there, guys, about people getting in equipment like that, striking power lines, and then jumping out and actually touching. You know, people don't understand ground is it's a pretty good conductor. It does have resistance, and if you get a power line that's down, the area around that is actually energized. So that's talking about staying in there if the thing catches on fire, comes out, and keep your feet together and do bunny hops. don't stride, because they talk about the distance between the stride could actually be enough to get enough tension off the ground. So guys, that's pretty it on safety that we're going to talk about in this class. And like I said, there's all types of videos. If you want to see people getting killed and electrocuted, you're the kind of person. Like Facebook, they keep popping these videos on there about, what do they call it, pimple doctor or something. But she's always popping big old sieves and squirting all this stuff out. That seems to be very popular on Facebook now. Where I see people popping that stuff up there all the time when people got a big old cyst on their head. So, it's about time for class to get it. What class ends at 1 or 1:30. So what we'll do next class is we're going to do a lab, play around with lockout, tagout. That's another thing we like about the amateur line. It has that feature. We're going to have to come up with some method to lock and tag the Festo line. So that Festo line doesn't have stops on it. Huh? No. What we got on that one is there's no main disconnect. There's actually no main disconnect on the amateur line. But it has one power plug. So we literally could kill power at the outlet. But we've also got a plug-in cord lockout that you can actually put the plug in and lock it. But the Festo line's got individual power supplies for each.
So you have to have the key code?
No, the key is used to switch it between manual and auto. Now there's a version of it that supports e-stop, but undoubtedly when I was looking at the documents, they talked about it. Then they talked about it being optional.
I was going to say, if the key turn off, you got a lockbox.
Yeah.
You just hang the lock in the lockbox, put the keys in the lockbox.
But no, those keys are not so we don't have the ability to lock and tag. And well, it's only a 24-volt system.
Still, usually, nowadays, everything manufactured is locked out.
And we got our the Festo line. We've had it since I think we got it in 2007.
Really?
Still pretty good shape. The
Where
Amtro line.
was it at?
It was over when we originally got it. It was over in the Milltop, and then we got the robotics slab. 2008 when I had my accident. That's when we got the robotics slab. I left when they were building, putting it together, and when I got back, it was already there.